Hello, everyone. So today we're going to talk about simulating the orbit of the Earth around the Sun with the Moon. So mainly with this moon in this case. So let's get started. All right. So common problem in physics is we want to model the orbit of the Earth around the Sun. Though that is very simple and very basic, but it's a great idea to understand how orbits work and everything. But the next step is adding complications. Common com- common things that you can add to complicate things are their planets. But in this case, we're just going to add the effects of Earth's moon and seeing how it orbits the sun and the Earth, as long and with the Earth orbiting the sun. So that's the complication we're going to add today, and that's what we're going to go through. So start off, we are just going to be dealing with the orbits, just if it was the Earth and the sun. And so I'm going to start off this first equation right here. And so the first equation, we have the mass of the Earth times the velocity of the Earth squared divided by r, or the distance away that object, in this case Earth, away from the sun. That's what NDR is going to stand for the problem. Equals the force of gravity. So if that's the force of gravity that the sun is having on the Earth, so that's that attraction force. Theoretically, there should be a negative here, but it's not super important right now. Um, that equals the gravitational constant of g, which is the mass of the sun times the mass of the Earth divided by r squared. So this is the most common form that you see this equation in, but there you also can see in this form. But knowing this form makes a really interesting substitution that we can make to make our units a little nicer. So understand in this form, we're in kilograms and newtons and more units and more stuff that we can mess up in larger numbers because g is something to 10 to the power of 10 to the power of to the negative 11th. And masses get really, really large. And so what we can do is we can do the substitution down here. We have g and m, right? G in the mass of the sun equals v squared. All right, you can see that already. Equals 4 pi squared, which is really nice because it just gives us an astronomical units, which is the distance of the Earth and the sun at parallelium divided by a year squared. And in that substitution, we can get that the acceleration in the Earth is equal to negative 4 pi squared over r squared if it was just the Earth and the sun. So that's really nice to know. Now, what we can do is we need to add the complication of just having with adding the complication of the moon. So next slide is we have the orbit equation with the moon. So as you can see here, we have two terms. We have this term and this term. This term is the term, this term, the one that we discussed last time. So very similar with the astronomical unit substitution. Now, this term over here deals with the additional gravitational force that the moon has on the Earth, or in reverse terms, that the Earth has on the moon in its orbit. So we're doing the 4 pi squared to keep our units simpler, just using astronomical units. And then we have the distance that the moon is from the sun minus the distance that the Earth is from the sun times the mass of the moon divided by the mass of the sun times the divided by the distance that the Earth is from the sun, that cubed. So that's the moon part. It's a lot to say out loud. It's much easier to type. That is the moon term right over here. Um, if we wanted to find the acceleration of the moon, you just would swap the Earth and the moon, change this to the Earth, and then also change this to the moon. So that's all you would have to do. I cannot draw. That's all you would have to do in this case. So now the next important step that we got to do is, due to the simplifications, we have to pick the coordinate system that we're going to graph these in. I'm assuming that we're going to be in a 2D plane, means that we should graph in XY components to make math a lot easier. So as you can see, we have the same terms over here. The only differences that we have are just that these are going to be the X and Y directions. That's the only difference that we have. So nothing too complicated here, but yeah. So the next step that we got to do is figure out the computational method that we're going to use to model the system. And the computational method that I would recommend using for modeling the system is the fourth order Runge-Kutta. You could attempt to do an Euler's method or a second order Runge-Kutta due to the fact of can propagate very quickly and air can blow up really quickly inside of an Euler's method and a second order Runge-Kutta. This is just more stable. So, and if you're already doing a second order Runge-Kutta, it's pretty easy to expand to a fourth order Runge-Kutta. So it's just the computationally a little bit more taxing. So for fourth order Runge-Kutta, I'm not going to spend a ton of time walking through this, but this is the equation that we have for it. And so, yeah. Now, the nice thing about a fourth order Runge-Kutta is you have to figure out the solution to the differential equations, which goes back to these equations over here, right? We got the acceleration, which also could be dvx over dt. And so if we want to head over to the next slide, we see that this is the solution for the Runge-Kutta for the derivatives and for the derivatives that we have to take here. So we know that the velocity is equal to velocity. The velocity is equal to the velocity in x, and that the derivative of the velocity is equal to that equation that we talked about 2 slides ago. They're the same thing, but it works really well. The one thing you have to be a little cautious of is this is highly sensitive to your initial conditions. And so if you're having errors, then your initial conditions are due to this. It's due to your initial conditions, and your math is okay. You just got to make sure you tweak them and that they're correct. So that's the solution to the Runge-Kutta equations. So now let's talk about the results. So as you can see, I graphed in astronomical units. So terms of 1 and -1, and 1 and -1. And it's very circular, which is great. So we see that. And in this one, it's really hard because we can see very clearly the path of the Earth, but we struggle to see the path of the moon. You can slightly see that there's some deviation. So go to the next slide, we can zoom in, and now we can really see the deviation that the moon takes and see how kind of the phases of the moon, right? Because it's kind of like this little sine function here that kind of goes back and forth. So you can basically say like over here, you have like, we'll say we have Earth right here, and then we have the moon over here. But right over here, the moon is over here as Earth is over here relative to each other. And so that's what we can really see is we can see the fluctuation of the moon's position relative around the Earth. Where is it in front? Is it in between the Earth and the sun, or is it on the other side? So like over here you have the new moon, and over here you have the full moon phase. So that's what we're really trying to get after here is seeing that new moon versus full moon phase. So yeah. Yeah, so thank you. The links in the description will be a link to a report. Will be a link to the GitHub that has code for this and a full-on document report for this. So, all right. Well, thank you, and I hope you have a wonderful